So going back to this slide here, where we have the structure of the liters. So we have in the liter number 3, 4 only. That's liter number 3 here, 4 pups, and liter number 3 actually has the control treatment structure. Liter number 12 has 2 pups, and they have the high-low, and similarly liter 23 has 3 pups high-low. So let's see how the variance covariance structure here works. Specifying its individual 3 we're looking at, and its type marginal. So the way this works is this. In the variance covariance matrix over here, along the diagonals, what we're going to have is the total variance in this, which is going to be sigma squared for the error term here, plus also sigma squared for the liter. Now given that in this liter number 3, go back a second, we have the control treatment structure, this should be sigma squared control. And the off-diagonal elements, because they now deal with the liter itself, the liter level variance, will be simply sigma squared liter. So you'll have this total symmetry in this matrix. The diagonal elements will all be the same, and the off diagonals will all be the same. So you can check the calculations to make sure that's how it works. Remember how it works, that it's sigma squared liter plus sigma squared control, and sigma squared control essentially is just sigma squared the error variance, and down the diagonal that's all constant because there's nothing much changing here in that sense. Same control is applied to all the pups, and the off diagonals are sigma squared liter. You can have a look at the same thing in this one here. Again, you will find this is a 2 by 2 matrix, and this is individual 12, and individual 12, this is cluster number 12, or liter number 12 here. Number 12 had the high-low structure, and so what you'll find here is that the diagonal elements is going to be sigma squared high-low, and this is, and then we're going to have sigma squared liter here as well. And the off diagonals are still sigma squared liter as in the previous matrix, so that doesn't change. And this is a 2 by 2 matrix, so again we have symmetry there. Now you can check, of course, sigma squared high-low was going to be the sigma squared error multiplied by the factor, the constant factor term. I'll go back a second to point that out here. Couple of slides here. And that's the high-low factor. You need to multiply that with the variance term. Go back another slide actually. Go back another slide. You have to multiply this high-low factor, square that, and multiply it with the residual variance squared. So multiply those two together, square that, and that gives you the variance for the high-low. So that's the number that goes in here. You can check those numbers, and you should do that. And the rest, the sigma squared liter is the same. This next matrix here is for liter number 23, which has 3 pups. And you'll find, because this is just an extension from 2 to 3, but it still has the same high-low treatment structure, this matrix is the same as this matrix here, except a bit bigger. So the diagonal is the same, and the off diagonal is the same as well. You can do this for every liter you have, and you'll find the same structure will appear, either as the ones that have control structure will have this structure here, either smaller or bigger, or those that have the high-low structure will have this structure here, just smaller or bigger. And here's some of the structural information. You can have a look to see what's going on there as far as the sizes of these things are concerned. You can look at that side yourself. So we have in the red pup example, if you look at the correlation, all that means here is you're going to just normalize everything by the variance covariance entries, and so you should be able to get these numbers over here. So that is essentially, if I go back to the matrix I had over here in this stage, all I'm doing is normalizing by the diagonal elements over here to essentially get a correlation matrix from there. And then similar for the other two that I've got in here. Okay, then if you take a look at the conditional model, so the conditional model here essentially takes out the effect of the liter, if you like, and we're looking at just the pup level. And so this is nothing more. If I'm taking a look at here, individual liter 3 over here, this is going to be sigma squared control, which is essentially the same as our sigma squared error. And because this is the high-low treatment, this is the sigma squared for treatment, high-low. And likewise, the last one is the same. So that's how the structure here works. That's enough of the red pup example. We'll now take a look at the same kind of detail for the classroom example. There's a bit more mess involved here at some stages, so we'll do a little bit of this and stop and then do it in the third lecture. So here, the model we fitted was that the maths gain was a fixed intercept. Then we had the classroom effect and the school effect and the class within the school effect. So this is the school random intercept, and this is the class within the school. So each of those random components will have mean 0 and variance accordingly, either school or class. And of course the overall error term here is going to be normal 0 variance sigma squared, and we are assuming that all the error terms are independent. So the ICC here, as we said, for the school level, so we have here the school, and underneath that we have the class, and then underneath there we have the students. So at the school level, the ICC is going to be the sigma squared for school as a ratio of all the other variances at that level or below that. So it's sigma squared school plus sigma squared classroom plus sigma squared the error term. And that's how this works. If I'm looking at the class level, then it's going to be the, as we'll see in a second, the same kind of idea will apply. For the classroom level, what we have is proportion of total random variation due to random between schools and between classroom variation. So it's going to be, when you take a look at the classroom level, what you have there is, you take a look at the variation at least in everything above. Now here, of course, the school level, there's nothing above that, right? So that's why it's the school level and everything below there. But here, it's going to be classroom and everything above that as a ratio of the whole lot. So it's the classroom and the school level over the whole lot. Because if you see, classroom is actually nested within school. And that is why we have to add both of those together. So those ICCs can be worked out fairly simply. And if you look at how they worked out here, it says here, if I look at the variance here for the maths gain IJK, now this is a bit of maths involved here. So the model actually is this. So the model here is actually, as we see this here. Now, the beta naught is a constant term. It doesn't have a variance. So that just drops off. And looking at the rest of them here, we assume they were independent here. So the variances simply add. And so the variance of the UK, which is the school, and the class level, and the constant, and so they all add up. If I look at covariance between two students in the same classroom, in the same school, so here the students are I and I dashed, the class is the same and the school is the same, so the other indices remain the same, only the I changes from I to I dashed. So you can see what's going on here. Again, the beta naught is a constant, it doesn't have any variance, so that drops off. And then I'm going to have a pairwise breakdown of what's going on here. So in the first term, I've only got the beta naught dropped off from the first and second. So it's a pairwise correlation covariance here. So it's UK with UK. It's UK with the whole lot, in fact. And then it's the UKJ with the whole lot and the epsilon IJ with the whole lot. So here, pairwise, I'm going to have that something, a covariance there. But because I assume that everything was independent, and this drops off and this drops off, all I get is the covariance with UK and UK, and the covariance of UK with UK is its variance, which is the school level variance. In this next term here, when I'm looking at the this second bracket over here, when I'm looking at the covariance of the UJK with everything else. Again, because of independence, and that drops off, and that drops off. So now I have is JK with JK, which is the class level variance, which is this here. So variance, covariance of something within itself is the variance. And the last one here, again, I will assume dependence. This is independent of that and that. And of course, this epsilon ijk are also independent of each other. So that also drops off. In other words, this last term gives me nothing. That's just going to be 0. So all I get here in the end is just sigma squared school plus sigma squared classroom. This is when I'm looking at two students together from the same class in the same school. And that's why there's the top line. And when I look at the bottom line, then if I look at two variance covariances between two pupils in different classrooms but in the same school, different classrooms in that case. So what will happen is different students, so the I's and the J's will be different. And if you work with the same thing in the same way as before, you'll find, if I just quickly go through this, let's be to note, let's be to note. So the UK with the UK will give me something, that's the school level. But the UK with everything else will give me 0, because there's nothing here that it corresponds with. Because of independence, the UK with UJ-K and the last other term will be 0, and everything else here becomes 0. So you can work through that if you wish, and you can ask me afterwards. But this gives me the school level if I'm looking at two students in different classrooms but in the same school, because that's a school level thing essentially. So if I'm looking at what's going on here as far as the variance covariance matrix is concerned for a particular class, in this case, students in a particular class in the school, then what I'm going to have here in the diagonal is this class, the school, and the pupil. But then when I take a look at this, the next one is just going to be school and class, because people has dropped off. The school and class, and here the same diagonal structure. And then I've got another block structure here, which is exactly the same as you'd expect, because this happens in blocks here. So essentially I've got a student in a classroom here, and I've got a classroom with, so this is 1, 1, 2, 1, 1, 2, 2, 2, 3, 2. You can see how that makes sense here. So the way this is looked at is student and classroom. So I've got this is student 1 in classroom 1, student 2 in classroom 1. So this is one classroom, and then I've got here student 1 in classroom 2, 2 in classroom 2, and 3 in classroom 2. So as long as in the same school, what I'm going to have here, the student classroom and sigma squared there, the same here. But this is block structure because of the 3 by 3 or 2 by 2 as I've got here, according to the classroom I'm in. So notice, of course, as I said, the block structure here, the diagonal, this is just school level, because I've got classroom 1 here and classroom 2 here. And so this is what's happening with classroom 1 and 1, classroom 1 with 2, classroom 2 with 1. So 2 and 1 here, because of the independent structure of the error terms, all I get is a school level block over here, and again here also the school level block. So this is just requires a bit of thinking, make sure you get it, but everything else is the same as far as the other blocks are concerned, the diagonals are concerned, because I'm in the same school and I'm with the classroom level as well, variance there. If I take a look at the correlations, then all that happens is I divide by the diagonal elements and the diagonal elements of the matrix. So that's going to be just this term here, that's the diagonal element that's common, and divide the whole lot by that, and you've just normalized that to a correlation matrix. So here is the output from the modeling, the data as we had before, the model as we fitted before. Now just be careful here to see what's going on. This is the school ID, the school random effect, so this is going to be sigma school, and this is class within school, so this is going to be sigma classroom, and this is our sigma overall model error, and we've seen this before. Nothing different here, the same numbers come out here, but now I'm looking at variances. So you'll see the variances are squares of the standard deviations. We've still got the school, and the class within the school, and the overall error term. And so the ICCs, as we said, at the school level is just the school variance over the variance of the whole lot, and the classroom level is classroom and everything above that over the ratio of the whole lot. Now the value here is quite small, which essentially means the schools aren't very much similar. They're not very similar, and neither are the classrooms, even within school, very similar. Now we can take a look at this patterned covariance matrices for random effects, and the common ones we saw earlier that the LME package provides are these ones. This block diagonals are a very common one, and we can also use simply diagonal over the compound symmetry structure. We've seen all this before. Let's see which one we fit here. The one we're going to fit here. So this data we've seen before, and just to remind ourselves, there were 107 schools altogether. The model we fitted in the end was here, with the random effects over here for classroom and for the school as well. And this was just math knowledge, the design matrix for the fixed effects, and the other bits and pieces are all the same here. Covariance here, as you would remember from earlier, were all to do with the school and the teacher and the classroom and so on. So I won't look at the details anymore. They were all together. It's a 313 by 313 matrix of random effects. And this is altogether the number of, because the random effects here deal with classroom and school, and this is the number of schools in there. So 313 random effects for the model we've got, and of course there is the residuals as well to look at. So specifically, this is what we're looking at here. This is the observations YK here for the kth school, and we've got the schools, classroom within the schools, and so on. The D matrix is just the diagonal matrix of the classroom effects, and there's a school effect here as well, depending on the school we're looking at. And this is going to be the 312 classrooms in altogether from all the schools. And you can run the matrix we have already here. And all the bits and pieces you will find will match up if you look at this carefully enough. So, we've seen this before. The random effects are going to be normal, as we saw, with mean 0 variance G here. Epsilon is also normal, 0 with matrix R. And both these matrix G and R are block diagonal matrices. And we can estimate them as we go through here. This is the model that's fitted over here. The first model here, as you can see, is simply the model with the random effects for school within class, with classroom within school. And then we have this other one where we actually have the random effect is the same. Well, it's school with the constant term here essentially, and also the class ID, the class term here as well. So in both these cases, the block matrix we have here is diagonal for each of the classrooms and then for the schools and classrooms. Now, when we look at the actual structure of the matrix, we'll see what we get over here. So here, the first one is for school 1. You'll find school 1 has 2 classes. One class has 3 children, and that's this block over here. And the other has 8 children, which is this block over here. So what you're seeing here in the off diagonal here is this is, if I call this class 1, and I call this class 2, so for those 2 classes then, what you will find is that the diagonal elements in each case will be the same as you can see from here. And that diagonal element over here is going to be sigma squared for school plus sigma squared for the classroom plus the error term. That's the first one. Then outside terms here, this is going to be sigma squared school. And then the off-diagonal elements over here are going to be sigma squared school plus sigma squared classroom. So with that structure, you'll find the block matrices are exactly the same for class 1 and class 2 as you expect, but the off-diagonal elements, of course, then will drop the variance, this random variance term altogether. So again, this is sigma squared school. That's sigma squared school plus sigma squared classroom, and that's sigma squared school plus classroom plus sigma squared. This is the same as the structure we saw earlier when we looked at the variance covariance matrix a little while ago. Let me go back and show you the slide. And here's the slide we're looking at. Back on the most slide here, yes. So you've got class from class 2. This is the overall variance term we've got here, some of the variances, some of school and classroom, and then just school over there. Then all we've done here is gone back and worked out the correlation matrix, which is found by essentially dividing the entire matrix with the diagonal elements, and the diagonal elements we saw were the same. And finally, for school, this is all we're getting here is the variance covariance for the school, which is school 1, which is essentially this RI conditional, which essentially is going to be sigma squared, the error term. If I look at the next class, exactly the same thing happens. For school 2, there are 3 classes, so you'll find 3 blocks here. That's the first block. And there's another block over here. I'm just going to look for exactly, it looks like it divides over here. You can see where it is, finishes over there. And that's the next block, next class. And this is the third class. So you'll find it has exactly the same structure as before. We still have the sigma squared school plus sigma squared class plus sigma squared there. And the off diagonals here are going to be just sigma squared school plus sigma squared class, and this is just sigma squared class. The same structure as before. From there, we take a look at the correlation matrix, dividing by the diagonal elements gives you this, and then again here this is just the diagonal elements of the variances over here with the conditional model. Now, that is all I'll cover here. This is for the more mathematically inclined. This is a bit more mathematics involved here. Here we actually look at estimating the model. So we'll look at things like likelihood estimates. I'll go just a bit further here. All the assumptions for the model are here. Now, this is the log likelihood, and so on and so forth. I leave this out for those who understand this. Have a look at this. Otherwise, I won't say any more about this one. That's enough for this week. Thank you. Bye.